In the ever-evolving landscape of machine learning, new techniques and methodologies continually emerge, aiming to enhance the efficiency and effectiveness of models. One such intriguing approach is speculative decoding, which has garnered attention for its potential to accelerate the decoding process in artificial intelligence tasks. In this blog post, we will explore the concept of speculative decoding, its underlying principles, applications, and the implications it holds for future advancements in machine learning. To appreciate the significance of speculative decoding, it's essential to first understand the decoding process. Decoding is the mechanism through which a model generates output sequences from encoded inputs. This step is crucial in tasks such as machine translation, text summarization, and dialogue generation. Traditional decoding methods, such as greedy search, beam search, and sampling, involve generating tokens sequentially. While these methods can yield high-quality outputs, they often suffer from inefficiencies, particularly in terms of computational time and resource utilization. As machine learning models, particularly those based on deep learning architectures, grow in complexity and size, the demand for more efficient decoding strategies becomes paramount. Traditional decoding methods can become bottlenecks, especially when dealing with large-scale models or real-time applications. In scenarios where speed is of the essence, such as conversational AI or real-time translation, finding ways to reduce latency while maintaining output quality is crucial. In speculative decoding, the goal is to generate multiple candidate outputs quickly while maintaining high quality. This is achieved through the collaborative functioning of two distinct models, the draft model and the target model. The draft model is responsible for generating a diverse set of candidate sequences in parallel. Its primary objective is to explore various possibilities without being overly concerned about the accuracy of each generated output. The draft model operates with a focus on speed and creativity, allowing it to produce a wide array of potential sequences rapidly. The draft model may use a less complex architecture or operate with fewer computational resources to expedite the generation process. In contrast, the target model is focused on quality and refinement. It takes the candidates generated by the draft model and evaluates them based on their likelihood and relevance to the specific task at hand. The target model aims to select the best candidates for further processing or final output generation. The target model is typically more sophisticated, employing advanced techniques such as attention mechanisms or contextual embeddings to assess the candidate's quality. This two-step approach, first generating a pool of candidates and then validating them, enables more sophisticated handling of token generation. It leverages the strengths of both the draft model and the target model, allowing the system to benefit from the speed of the draft model while ensuring that the final outputs from the target model are reliable and of high quality. By implementing this strategy, we enhance the overall effectiveness of the speculative decoding process, making it a powerful tool for various language generation tasks. Initially, we input the data into the draft model to obtain the next K tokens. There are various methods for generating these tokens. The most straightforward approach involves generating each token sequentially, one at a time, as is typically done. Alternatively, we can generate the next K tokens simultaneously using a method known as Medusa. This approach allows for the concurrent production of multiple tokens, which can enhance efficiency and speed in the drafting process. Once we have a set of candidate tokens generated by the draft model, we proceed to pass all of these candidates to the target model for evaluation. Unlike the previous token generation phase, where tokens were produced sequentially, this time we can utilize a more efficient approach. We conduct a single forward pass through the target model to assess whether each generated token meets a predefined threshold of quality. During this evaluation process, the target model checks each candidate token against specific criteria. If a token successfully passes the threshold, it is accepted and incorporated into the final output. However, if a token does not meet the quality standards set by the threshold, the target model will regenerate that token to ensure the overall integrity and quality of the output. This mechanism allows us to maintain a balance between efficiency and quality. By verifying multiple candidates in a single forward pass, we streamline the process and reduce computational overhead. At the same time, the option to regenerate tokens that fall short of the threshold ensures that the final output adheres to the desired quality standards. By separating the roles of candidate generation and evaluation, the system can produce outputs more quickly. The draft model can focus on generating a wide range of possibilities, while the target model can evaluate these options without being bogged down by the initial generation process. The parallel processing capabilities of the draft model facilitate the exploration of multiple sequences simultaneously, significantly reducing latency in generation. This is particularly useful in real-time applications where rapid response times are essential. Integrating the two models can introduce complexity into the system. Ensuring that the draft model generates candidates that the target model can effectively evaluate requires careful design and tuning. Both models need to be trained adequately to perform their respective tasks effectively. This may involve using different datasets or training paradigms, which can complicate the overall training process. Speculative decoding represents a significant advancement in the quest for efficient and effective decoding strategies in machine learning, particularly within the realm of natural language processing. By leveraging parallelism, dynamic evaluation, and early stopping, this approach has the potential to revolutionize the way models generate text, offering faster and more contextually relevant outputs. As research in this area progresses, we can expect to see further innovations that will enhance the capabilities of machine learning systems, ultimately leading to more responsive and intelligent applications across various domains. As we continue to push the boundaries of what is possible in AI and machine learning, speculative decoding stands as a promising avenue for exploration and development.